In section 7.4, there's a general approach to integrals with some forms that involve the sum or difference of two squares. And in our abbreviated semester, we're not going to have time to do all of this, but I do want to just show you the type of thing that we do in this section, because the idea of substituting, moving between measurements in the rectangular coordinate system and measurements of angles is something that those who go on to Calculus 3 will pick up and do quite a lot of. The other reason for doing it is that it's a little weird that we get all the way to the end of a second semester calculus course before we have enough calculus tools under our belt to find something as simple as the area of a circle. But that's what we're going to do. The first integral here that we have as an example, the integral of square root of 9 minus x squared, if I draw a picture of that, that would be a quarter circle of radius 3. So this integral is finding the area of that quarter circle. So it's a little strange that we learn area is pi r squared probably in elementary or middle school. But in terms of being able to prove that that's really true, using the tools of calculus, it takes till now before we can do that. So the key step here is, like I said, the idea of moving between our traditional coordinates in x's and y's and changing a problem over to be written in terms of measurements of angles with trigonometry. So I'm going to just resize the screen, give myself a little more space, and I'll even cover up this mess so that I have room to write. So the centerpiece of the story is just a conversion between angles and straight line measures, and we do that with our basic trig functions. So what I want to set up here is a right triangle. My motivation is this expression right here, this 9 minus x squared. So what I want my right triangle to have in it is one side labeled with something involving 9 minus x squared. And I can do that by making my hypotenuse 3 and my side opposite the angle t using the letter x. Once I have that, then we can figure out the third side of the triangle using the Pythagorean theorem, and that would look like this. The mystery side, the leg squared plus the other leg squared equals the hypotenuse squared. That's the Pythagorean theorem. And so if I want to know what that mystery number is, I could subtract x squared from both sides. Well, not 9 squared. 3 squared. Subtract x squared from both sides, and then take the square root of both sides, and I will have, as my mystery number, I'll have square root of 9 minus x squared, like that. Just a quick cautionary word for those of you whose algebra skills are a little fragile. That does not simplify. You can't distribute the square root sign through those terms, so it's not the same as 3 minus x. Square root of 9 minus x squared is as good as it's going to get. And so this actually ends up being great for us for this problem because it wasn't really just the 9 minus x squared that we wanted. That was kind of the motivation of picking those values, but we literally want the square root of 9 minus x squared in this integral, and it's right there. So what we're doing here is going to be a substitution, and the substitution will feel a little bit different because we want the substitution to reflect the right triangle that I just drew. So what that right triangle tells me is, for example, the sine of t is x over 3, using my the sine of t as the opposite over the hypotenuse, and the cosine of t is the square root of 9 minus x squared over 3. So these equations about the relationship between x and the angle t are going to be the heart of the substitution we're going to make. So I know that if I'm going to substitute into an integral, I not only have to substitute x for the new variable, but I also have to substitute the differentials the dx and the dt in this case. So let me get that first. This first expression that I have here is the easier one to work with. So I'm going to rewrite that as x equals 3 sine t, so I don't have the fraction in there. And then I'm going to take the derivative of both sides with respect to t, and I'll have dx is 3 cosine t dt. So this will be my relationship between my relationships between x and t, and then also between dx and dt. So we call this a trig substitution, and it is different than the other kind of substitutions we used, not in technical sense, but in the way we feel about it. Before, when we did a u substitution, we were always letting u equal something complicated in our integrand with the hope of getting some complicated part of our integrand to collapse into something easier. This has the exact opposite effect. Here we're taking a substitution that changes the single letter x into something quite a bit worse. And so when we do that, it's going to make this integrand be a lot worse. But it's only going to be worse for a minute, and we then can use trigonometric relationships to simplify it. So here's what that would look like. I'm just going to try to substitute equal for equal into my integral. So I'll start with the dx part, because I know that has to happen. So the dx part is going to become 3 cosine t dt. So that's dx. The part with the square root sign, this is the part where drawing this triangle at the beginning can really help. Notice that this expression right here is part of this expression. And so I could change the x into sine using this thing and then do some trigonometry, but I could just say, well, I recognize that from my trig relationships with respect to this triangle. So this part right here is actually 3 cosine t. So I'm not going to waste our time by doing it a different way. I can see that 3 cosine of t is the same as the square root of 9 minus x squared. So that part, this part of my integrand, is just going to become 3 cosine t. So altogether, I have 9 cosine squared t dt. Now I didn't carry the limits of integration with me through this, and I definitely want to do that for these kinds of problems, because it does become much more of a pain to substitute back at the end with trig substitution. So remember, when we're trying to substitute back, we know that this 0 and 3 are in terms of x. So that's x equals 0 to x equals 3. That's what those limits of integration mean. We know that this is the relationship between x and t. So all I need to do is for each one of those, figure out what the corresponding value of t should be. And so I can just do that one at a time. When x is 0, I mean, if this is 0, I'll have 0 equals 3 sine t. So in other words, sine of t is 0, and the only, well, not the only value, but if I take the inverse sine of 0, I'll get 0. One problem with these reverse trig functions is that there is more than one value. So we'll take the principal value, the value that the arc sine function gives us. So if on your calculator you do inverse sine of 0, you'll get 0. Similarly, if x is 3, and you put 3 right here, then 3 equals 3 sine t. That only happens when sine of t is 1. And if you ask your calculator what the inverse sine of 1 is, it's going to say pi over 2. Presume you have this set on radians. So the limits of integration, once we've transformed our integral to being in terms of t, our limits of integration should be like that. Notice this is now an integral using powers of sines and cosines. In this case, it's just cosines. And so this becomes a problem exactly like every problem that's in section 7.3. In fact, this is the first example that we did when we did the problems from 7.3. The first video from 7.3, this was one of the problems. So I won't repeat the process here, but the antiderivative was 3 times t over 2 plus 1/4 sine 2t. And that's going to get evaluated from 0 to pi over 2. So let me give myself a little more space here. Oops. And so finally, I'll have 9 times pi over 2 over 2, that's pi over 4, plus 1/4 sine of pi, minus 9 times 0 over 2, plus 1/4 sine of 0. And so the sine of 0 is 0, the sine of pi is 0, and so what we get in the end is 9 times pi over 4, which is exactly the correct area for this picture. This is 1/4 of a circle of radius 9. We know that a complete circle of radius, sorry, not radius 9, radius 3. We know a complete circle of radius 3 has area 9, 3 squared, and this is 1/4 of that. So 1/4 of 9 pi is exactly what we thought we would get for the answer to that area question. Here's a second example of trig substitution, and this one is probably the most complicated one that we'll see. So you can kind of see the other extreme. It looks very similar to the one we just saw. It has more stuff going on in it. The key thing is that we want to first label our triangle so that the identity, or at least the key component of this 9 minus 4x squared comes up because of the Pythagorean theorem. We've seen that can be helpful, so we'll set our triangle up to have that happen. So to do that, I'm going to put, I don't want yellow. I'm going to make the opposite side here be 2x and the hypotenuse be 3. I'm always going to make my hypotenuse be a constant number, and then the side opposite t will be the thing that has x's in it. But if I do that, just like before, we can do the Pythagorean theorem and see that the third side that we don't have an expression for, squared plus 2x squared is equal to 3 squared. And the most important thing here is to make sure you're putting these things in parentheses, because we really are going to square 2x. So 2x times 2x is 4x squared. 3 times 3 is 9. And so if you solve that for the missing leg, we'll have the missing leg is the square root of 9 minus 4x squared, which is exactly the expression in the integrand that we're going to try to substitute away. So that leads us to believe that we are on the right track. So 9 minus 4x squared. And then the trigonometric relationship between the variable t and the variable x comes from the sine and cosine rule. Sine of t is 2x over 3, and cosine of t is square root of 9 minus 4x squared over 3. Now to do a substitution in an integral, I need to know how to change x's into t's and how to change dx's into dt's. So I'll do the same thing I did last time. I'll take the first equation and I'll rewrite that so that it is in terms of x. So I'm solving the first equation here for x. So x is 3/2 sine of t. And if x is 3/2 sine of t, then I can take the derivative of both sides with respect to t. I'll have the differential dx is 3/2 cosine t dt. So those are the two things I'm going to be using in my substitution. So let's go ahead and do it. In the numerator of this integral, I have x squared. And so remember, x is 3/2 sine of t, so that'll be squared. So that is the x squared part. The x squared part becomes this part. The dx is going to become 3/2 cosine t dt. So the dx part becomes that because of this fact. So I really am just trying to use these things as much as I can in my substitution. I'm still missing the part here. This is the square root of 9 minus 4x squared. And like before, I could try to make x equal to 3/2 sine t. I mean, I could try to do it from here, but if I've been paying attention through this process, I should be able to kind of short circuit it. The square root of 9 minus 4x squared is what I'm substituting. And notice right here, I have something that has square root of 9 minus 4x squared in it. So from this fact, I know that 3 times cosine t is square root of 9 minus 4x squared. So in my substitution, the expression that's in the denominator here becomes this. So I've managed, there are 3 different components of the integrand. There's the numerator, the denominator, and the dx. And I've replaced all of them with expressions in terms of t, all based on this triangle picture. Okay, so I'm going to erase the stuff below now so I have room to write some more. I'll leave this stuff here. Possibly in black. So my integral, I have, let me get my constants first. So I have 3/2 squared. So that's 3/2 times 3/2 times 3/2, and then divided by 3. So that's a lot of constants bumping around. But so 3/2 times 3/2 times 3/2, and then divided by 3. So I'll have 9/8 will be the constant that's left from doing that. This cosine of t is going to cancel with this cosine of t. And then all I'll have left is the sine of t squared in the numerator. Like that. The integral of sine squared is actually the integral that you did on the thing you handed in for, I think it was daily 9. So you've actually already done that problem. The integral was, the integral of sine squared was, it's not x, it's t now, hang on, was t over 2 minus sine of 2t over 4. And so that would be the result of this integration problem. The only issue is that that answer is in terms of t, and the original question was in terms of x. So it's only polite if the question is in terms of x, that we should give an answer in terms of x. And now you start to see one of the difficulties of trig substitution. It's not so much doing the substitution, that's actually pretty easy, but putting the variable back in at the end is more challenging, which makes sense if you think about what the process will be. So let's go ahead and do it. Basically, I'm working on the information I have over here, and I'm trying to get things written back in terms of t in terms of x. So the part that's just t, I'm really kind of stuck with. The only thing I can relate back to that comes from any of these, but let's pick the one that's easiest to solve for t. I have all of these things over here on the right, and I need to solve one of them for t. So let me do the one that's closest to being solved already is this one up here. So if sine of t is 2x over 3, that means t is the arcsine of 2x over 3. So in my integral formula, that t right there could be replaced with the arc sine of 2x over 3. It's not worthwhile doing that here. We can actually do better than that. So to get at this part, because it's a trig function of t, remember my t is defined by this right triangle. So if you ask me any trig function about this t, like tangent of t or secant of t or cosine of t, I can get that because I have all of these sides labeled. Sine of 2t, though, is a little trickier because I do not have a triangle that has 2t in it. I only have the one that has t in it. So the thing that'll save the day is knowing one more double angle formula. I'll hold off on making that substitution. The sine of 2t is 2 sine of t cosine of t. So that's the sine of a double angle. I'll write that down here. Sine of 2t. And this is not something about the substitution. This is just the formula from trigonometry. So let me just resolve all this parentheses, and then I'll be able to deal with it. So I have 9/16 t minus 1/2 sine t cosine t. Oops, I forgot my 9/8. Hang on. There's a 1/2 there, but there was also a 9/8 outside there, so. Okay, so now I've got rid of got the constants done. All right, so now I can just read off my sine and cosine. Sine of t is 2x over 3, cosine of t is this thing. So finally I'll have 9/16 arc sine 2x over 3, that's what t is, minus 9/16 the sine of t is 2x over 3. The cosine of t is this thing. And then plus a constant. So the only small thing left to simplify is that this is 3 times 3, and that cancels out with a 9. And I can simplify the 2 over the 16 a little bit, but basically, except for canceling out some of the constants, that's the answer. So that was the most challenging one that we have, and you can see that most of the challenge happens after we've gotten this answer, right? We are able to do this integral, and then after that, getting the x's back into the problem for these are quite a bit more complicated. That's why on the previous example, I mentioned that if this was a definite integral, then moving the limits of integration over to the new variable makes life a lot easier, because otherwise you got to go through all of this just to be able to plug numbers in at the end.